Activity 1. Sampling from a uniform distribution. And the objective here is to explore how sample means behave when drawn from a uniform distribution, demonstrating the principles of the central limit theorem. Now I'm going to say here that we're going to be working with a very small sample. We're going to be looking at n equals 4. Now n equals 30 is the golden thing to remember for exams, because you usually say that you need a large sample, n is 30 or more, in order for the central limit theorem to apply. But we shouldn't get too bad results from this, because one of the things that this uniform distribution shares with the normal distribution that we're tending to is that it's symmetric. So higher n's are really needed when we have asymmetric distributions, and we'll look at that a bit more later with the other activities. So materials needed: a deck of cards numbered 1 to 10. Use ace as 1 and remove face cards, or use ClassPad to simulate. Now obviously we're going to use the ClassPad to simulate, or more realistic really, we'll probably write a bit of Python to do it, and then we can run it really quickly on our computers. Pen and paper or a spreadsheet for recording results. Again, not really necessary if we use a bit of Python. Calculator or software for statistical analysis, and that's optional. We're not going to go too deep into this. So steps. Part A, understand the population. That's our uniform distribution. So define X is the value of a randomly drawn card from the shuffled deck, or if you like, a randomly generated number from your ClassPad. Theoretical distribution. Each number, 1 through 10, has an equal chance of being drawn. Complete a table for the theoretical probability distribution of X. And you can see I've done it here. All of the probabilities are 0.1 for 1 to 10, and of course those probabilities therefore add up to 1. Population mean and standard deviation. Calculate the mean and standard deviation of the population. You can do that, of course, on your ClassPad. Mu is 5.5, which you should know because it's in the middle, 10 plus 1 divided by 2. The standard deviation is 2.87, and that is rounded to 2 decimal places. Collect samples of size 4. So it says shuffle the deck thoroughly. We're not going to use a deck. Draw 4 cards randomly with replacement and record their values. Calculate the mean of the 4 values. Repeat this process 6 times to obtain 6 sample means. Record the data in a table like the one below. And here are my answers. So I got 3, 4, 1, 2, 4, 6, 4, 9, and so on. And then I calculated the means of those. Can't guarantee they're all correct, but because I didn't actually check again, but I think I got them right. And then we've got to analyze the sample means. So I've got a histogram for the data that we had up here, and we can see that it doesn't look very much like the original distribution, which would have been uniform, and it has moved more towards the middle. But obviously with a sample of 6 you're not going to see much. I would guarantee that when you look at other people in the class doing this, that everybody's got a different picture, or maybe 2 or 3 people might have the same picture. But if I do this again and again and again, I'm going to get a different picture. So there's not too many conclusions you can draw. It's also got a bit of a clusters and gaps sort of appearance, but that's what you're going to expect when you only have 6 samples. What you will notice though is it has moved away from the extremes of 1 and 10. Calculate the summary statistics is next. So find the mean and standard deviation of our sample means. Compare these to the population mean and standard deviation. So X bar is 4.75. Standard deviation is 1.28. And the one that's worth doing here is the population standard deviation divided by the new one is 2.24. The standard deviation is quite a bit less, and we talked about this in the introduction. we're moving away from those extremes. We've moved quite a long way with just a sample of 4. So now we want to increase the number of samples, but if we're doing this manually, it's difficult to do a very large number of samples. So repeat the process above, but this time collect 25 samples, which you can see I've done in this table here. And I did genuinely actually generate these samples and calculate them. And then I've got a frequency table here, and I meant to use the highlighter, of course. And you'll notice once again that they are clustered more towards the middle, like so. Notice that the highest bar is where the 5.5 population mean would be. You're not guaranteed to get that, obviously, with 25 samples, but it's just interesting. And then compare the distribution of the sample means with the population distribution. Well, the population distribution, we know, is uniform. But here we can see it's not. It's moved away from the extremes, and it is clustered around the middle. Now, it does not look normal, but nor does it look like the original uniform distribution. The spread is definitely reduced. The mean is 5.46, approximately the same as the population mean of 5.5. The standard deviation is 1.42 to 2 decimal places. That's about half of the population standard deviation. And those things will also vary if you compare them to other people doing the same investigation. So there's some discussion questions. Well, one of the questions is to do exactly that. Compare your results with those of other students in the class. How similar or different are your sample means, and what does this tell you about natural variation in sampling? There's likely to be some variation, there's a small n, and we're taking a small sample. How do the shape and spread of the sample mean distributions compare to the population distribution? The population is uniform. This one clearly isn't. As you increase the number of samples, how did the histogram change in terms of symmetry and clustering around the mean? And the advantage of the bigger sample, notice when I say the bigger sample, we're using n equals 4 throughout here, so each individual sample is of 4. We're talking about a bigger sample of samples. So the advantage of the bigger sample is we are far less likely to get clusters and gaps. Unrepresentative samples are likely to be a smaller part of the sample. When we only did 6, if we'd got a couple of really unrepresentative ones, it would have really affected our results. It is not uniform, and the greater frequencies are close to the population mean. I pointed that out when we had the table. Why do the sample means tend to cluster around the population mean? And how does increasing the sample size influence this clustering? With individual values, they can be anywhere from 1 to 10 with equal probability. That was the uniform distribution. But with a sample of 4, we need to get 1, 1, 1, 1 for the sample to mean to be 1, or 10, 10, 10, 10 for the sample mean to be 10. These samples are very unlikely, but there are lots of ways to get a sample mean of 5.5. Many, many more ways. And therefore, it's more likely that you get a mean that's near the middle.